Hi, this is Mrs. Basin, and today we're going to talk about LeChatelier's principle, which is section 15.6. So what this principle says that if you have a system in equilibrium and you disturb it or disrupt it by a change in temperature, pressure, or concentration of something involved in the equilibrium system, it will shift the position to counteract the effect of the disturbance or the stress. So basically, if you have a system at equilibrium and you do something that disrupts the equilibrium, it will shift to counteract that stress. So we're going to go through each type and talk about each type first, and then we'll look at some examples. So the first thing you can do is you can change the reactant or product concentration. So if you change the concentration of something, then what it will do is it will shift to reestablish equilibrium by either using up that reactant or product or replacing the reactant or product that was placed into the system. You can also change or shift the equilibrium if you change the volume and the pressure. So if you have gaseous products or reactants, changing the volume or changing the pressure is equivalent to changing the concentration. So if you decrease the volume of something, the pressure of the gas is going to increase, which, like I said, is equivalent to increasing the concentration. So if you increase the pressure, then it's going to shift to counteract that. So the last two bullets on this slide are important. So if you increase the pressure or decrease the volume, those two things have the same effect, that results in a shift to the side with less moles. That's how it counteracts it. If you have a decrease in pressure or an increase in volume, that results in a shift to the side with more moles. That's how that counteracts it. If you have a system that has the same numbers of moles of gas on both sides, then changing the pressure does not have an effect. And then also, if you introduce a gas that is not part of the equilibrium system, then that will also not change the equilibrium. All right, the last one we'll look at is temperature, and then we'll look at a real system here, and this will hopefully make a lot more sense. So if you change the temperature, you're going to change the equilibrium constant. We've talked about that over and over, that this equilibrium constant is temperature dependent. So when you change the temperature of a system, which direction it shifts depends on whether the reaction is exothermic or endothermic. So if something is endothermic, if you increase the temperature, it's going to shift the equilibrium to the right. It shifts away from where heat would be added into that system. If it's an exothermic reaction, increasing the temperature shifts the equilibrium back to the left, which again is shifting it away from where heat would be in that particular system. So let's look at an example here, and hopefully this will help make this make a little more sense. So this is something we're going to look at in class. This is a cobalt chloride complex. So when this starts out, it is this kind of purple color right here. Okay, so this is one equilibrium it could be at, where you have this purple color. So when we do different things to it, it shifts to the right or to the left. And this system is nice because you can tell whether it's been shifted to the right or the left based on what color you see for that particular, at that particular, under those conditions. So in this first example, the picture that we have here shows that you have a blue species, and then you also have a pink one here. So let's look at what happens when we get blue. So to shift it to this side, this particular one has been placed in hot water. So the way you can look at this is if you imagine you are adding heat to this system. So you are adding heat, and this is an endothermic system. So if you add heat to the system, it's going to shift away from the heat and shift to the right, which is why we see the blue. For this other one, the pink one, they've added ice to this system. So when you decrease the temperature, you can think of it as removing heat from the system by making it colder. So what it will do is it will shift to that side to replace what was taken out. So it's shifting back to replace the heat that was removed by cooling it. And that's why we see the pink. Okay, so then let's look at this again. Something else we could look at here, let's say we added Cl- to this system. So if we added Cl- to the system, it would shift in this direction to use it up. If I added, and this should be H2O over here, if I added water to this system, it would shift to the left to use that up. If I took water out, then it would shift back to this direction to replace the water. So again, you can see it's shifting to counteract the stress. So if you add something to one side, it's going to shift away from it to use it up. If you remove something from one side, it's going to shift in that direction to replace it. All right, so let's look at some example problems. So this is our equilibrium, and the reason they give us the delta H is because that's how we know whether it's exothermic or endothermic. So this particular one is endothermic because this has a positive value. So what that means is heat would be on this side. So I'm going to put heat into this equation. That way we can tell what would happen if we change the temperature. Okay, so the first thing we're doing here is we're adding N2O4. So if I add N2O4, it's going to shift away from that to use it up. So for this one, this would shift to the right. Okay, for the next one, if I remove NO2, that one's going to shift in the direction to replace it, so that would also shift to the right. The next one, I would increase the total pressure by adding N2. Okay, now if we look in the system, there is no N2 in the system, so adding a different gas that's not involved in the equilibrium system will not change it. So this would be a no change. If I increase the volume, I have to think about what I said when you are shifting depending on which side has more moles, which side has less moles. So if I increase the volume, I am decreasing the pressure, and when that happens, it shifts to side with more moles. So it's going to shift to the right. So it shifts to more moles, which would be to the right. Okay, and then finally decreasing the temperature. So decreasing the temperature would be taking heat out of the system. So if you take heat out, it's going to shift back to replace it. So that would shift to the left. And you will get lots of practice with this in class because this is what our lab that we're going to do over the next couple days is based on. Okay, so here's our reaction here. Again, it gives us the delta H value. So this is also an endothermic reaction. So I'm going to put heat over on this side so I know what to do with the temperature difference. Okay, so this one, first one, I'm adding Cl2. So if I add Cl2, it's going to shift away from that to use it up. So this is going to shift to the left. Next one, increase the temperature. So I'm adding heat. So if I add heat, it's going to shift away to use it up. So it's going to shift to the right. The volume of the system is decreased. So if I decrease the volume, that's increasing the pressure. So it's shifting to the side with less moles, which is shifting to the left. And then finally, adding PCl5. If I add that, it's going to shift away from it. So it will shift to the right.